Okay, so let's get back into this. Okay, so this next part is much simpler if you've internalized first-order kinematic coefficients. This is kind of analogous, but for an acceleration analysis. And this is, truthfully, if you do acceleration analysis on mechanisms, this is probably the best way to do it. That other stuff gives you a lot of insights about acceleration and allows you to do all sorts of neat things. But this is a more systematic and much simpler way to do acceleration analysis, okay? And it uses kinematic coefficients. So let's just review. Say you had a mechanism, you want to analyze it, do position analysis, you draw the vector loop equation, okay? Then you draw it in component form. Okay, there's your component form, and you do position analysis. I give you a theta 2, you solve for the two unknowns, theta 3 and theta 4. Great. Okay, and you do that by finding the Jacobian matrix of this mechanism and using that in Newton-Raphson to generate these things. Hopefully you wrote that code and you can find theta 3 and theta 4. Or you could analytically solve it, but like I said, it's not recommended. Okay? All right. Then, if you want to do velocity analysis, you take the derivative of the component form, not with respect to t, that would be a mess, but with respect to the input variable theta 2. And so we did this before. You take the derivative of that with respect to theta 2, you get this. Take the derivative of that with respect to theta 2, you get that. Okay, and from that, recall that the first order kinematic coefficient of theta 3, the output variable, or prime, remember, it's kind of confusing. Prime sometimes in this course means that a delta t later. That's not what kinematic coefficient land means. If you see a prime, it means the derivative of theta 3 with respect to the input variable, in this case theta 2. Okay, and theta 4 prime is the first order kinematic coefficient of the output 4, which is the derivative of that with respect to the input variable. Okay, in this case theta 2. Okay, and then remember what we did was, we pulled, we moved everything. It doesn't have the kinematic coefficients on the other side, pulled the kinematic coefficients out, and we found, lo and behold, there was a Jacobian matrix. That's the same Jacobian matrix you use for position analysis. You invert it and you find the kinematic coefficients. Then once you find them, you multiply it by the input angular velocity, and you get the output angular velocity, and you're done with velocity analysis. You've now found the omega 3 and omega 4. So that's a nice review, okay? Okay, but now say we've done position and velocity analysis, and I give you an alpha 2. I say, okay, but what if at that position of theta 2 and at that omega 2 that I gave you, with all that, I give you some alpha 2, and I want you to know what the alpha 3 and alpha 4 is of length 3 and 4. Well, to do that, let's do a little math and see what happens. Of course, we want alpha 3 and alpha 4, so let's take the derivative of this with respect to time, because that would give you alpha 3, d omega 3 with respect to t. Okay, well, again, the first order kinematic coefficient and omega 2 vary with respect to time. So you have to use kind of a product rule here. Okay, so you do the derivative of first order kinematic coefficient theta 3 prime with respect to t times omega, the normal one, plus the normal one here times the derivative of omega 2. Okay, so you get that. Okay, now recall from the chain rule that the derivative of theta 3 prime with respect to t is the derivative of theta 3 prime divided by the derivative of theta 2 times the derivative of theta 2 with respect to time, so the d theta 2's cancel and you get this. That's just chain rule, okay? But this is going to be useful because we can take this, all this stuff, and plug it in up there, and what you end up getting when you do that is, remember, d theta 2 with respect to time is omega 2, so you get omega 2 squared, and you get that. And then you add it to this stuff, which the derivative of omega 2 with respect to time is alpha 2. Okay, but now we know something interesting. If you take the derivative of the first order kinematic coefficient of theta 3 with respect to the input variable theta 2, you're essentially doing the double derivative of theta 3 with respect to theta 2. Because remember, the first order kinematic coefficient of theta 3 is the derivative of theta 3 with respect to theta 2. And if you take the derivative of that with respect to theta 2, it's the double derivative. And so we call this the second order kinematic coefficient, and we do 2 primes. Two little, it's like a quotation mark or something to show that it's derivative twice with respect to 2. Remember, if we take derivative with respect to time, we put a dot above it. If we take derivative with respect to the input variable, we put 2 little tick marks. Okay. Okay, so now we get to a super famous equation here, which is just this, where it's just alpha 3 equals, basically theta 3 double prime, or second derivative of theta 3 with respect to theta 2, or the first order kinematic coefficient, times omega 2 squared plus omega 3 prime times alpha 2. And we can do the exact same thing with alpha 4, okay? So this is akin to just taking the first order kinematic coefficient multiplied by omega 2 to find omega 3 or omega 4. But this is the acceleration version. So you should really memorize this. It's kind of weird. You take the second kinematic coefficient of the output, times it by the velocity, which they gave you for velocity analysis squared, the input velocity, plus the first order kinematic coefficient, which you solved for using... what I'm saying is what this says basically, which you already solved for velocity analysis, and then you times it by the new input alpha 2, and that will give you the two outputs, okay? So I can't emphasize enough, again, to do acceleration analysis, you need to have done position and velocity analysis, okay? Okay, so but the question is, how do you find the second order kinematic coefficients? How do you find theta 3 double prime or theta 4 double prime? Well, what you do, remember you had these component forms and you'd taken the derivative of them, the component forms of the vector, closed loop vector equation, and you took the derivative of them with respect to the input variable theta 2. And you got this, and this is where you pulled it out and did velocity analysis, right? Found those first order kinematic coefficients, times it by omega 2. Well, now instead of that, let's take the derivative of them again with respect to the input variable. So once you've already taken the derivative with respect to the input variable, but let's do it again for acceleration analysis. Okay, so I'm going to, put me on pause and see if you're a master of derivatives and take the derivative of that top equation with respect to theta 2 again. And don't forget to use the product rule. Okay, if you don't want to wait, I'm going to give you the answer. It's this. Okay, so just go through and make sure you understand, because theta 3 prime varies with respect to theta 2, and sine theta 3 varies with respect to theta 2, you do a product rule and you get these two things. And the second one, you get these two things from the product rule. So you got to get very good at this. Okay, so stare at these equations and make sure you understand the chain rule and the product rule, and you'll be able to get the double derivative. So take the derivative of this one now. So go ahead and put me on pause and do that equation with respect to theta 2. Okay, or if you want the answer, I'm going to give it to you right now. There it is. Okay. Okay, notice by doing this, you create the double derivatives of the kinematic coefficients. So you get the second order kinematic coefficients, and that's what we're trying to solve. So to do that, you can do the same thing we did with velocity analysis and take everything that doesn't have a second order kinematic coefficient in it, move it to the other side, and then pull out the second order kinematic coefficients and find a matrix. So why don't you put me on pause and do that? Like find a matrix equation that solves for the second order kinematic coefficients. So theta 3 double prime, theta 4 double prime equals something. Go ahead and put me on pause. But if you don't want to, I'm going to give you the solution. Here it is, okay? If you move everything that doesn't have those in to the other side, you get something like this. And then if you pull the theta 3 double prime, theta 4 double prime out, you get something like this. Now, this might trigger something because magically, once again, for a 4-bar, its signature matrix, the Jacobian matrix, pops up again. This is the Jacobian matrix of a 4-bar mechanism. Okay, it popped up in Newton-Raphson. You needed it to do that for position analysis. It popped up in velocity analysis when you're solving for the first order kinematic coefficients. And that's one confirmation that you're doing it correctly, if it's the same as the Jacobian matrix. And once again, it pops up in acceleration analysis. And so if you're doing this on exam and you do position analysis first, then you do velocity analysis, you do acceleration analysis, each time if you get a matrix that's different, you're in trouble, right? You've done some math wrong. So you can know you're doing your exam correctly if this same matrix keeps popping up, the Jacobian matrix, right? Okay, and then of course you can invert this and times it by that. Now you solve for theta 3, the first or second order kinematic coefficients. And I want you to notice this whole matrix requires position analysis to be conducted, as well as velocity analysis. Okay, so you already know R2, R3, R4, and you know theta 2 because that was given to you. But now you also need to know theta 3 and theta 4. That's position analysis. And you also need to know the first order kinematic coefficients. That's velocity analysis, theta 3 prime, theta 4 prime. So you know all this because you've done velocity analysis. You know all this because you know that you've done position analysis. And so from velocity and position analysis, now you're ready to solve for the second order kinematic coefficients. And you can now plug them in these famous equations that hopefully you will memorize. And you now know these. You know these from velocity analysis. You know these from velocity analysis. And they gave you this for acceleration analysis. So now you can calculate alpha 3, alpha 4. Okay? So it's very similar to first order kinematic coefficient analysis, but it's just taking these one more level for acceleration analysis. And you use this equation instead of first order kinematic coefficient times omega. Okay? So let's do another example. Here's the slider crank mechanism. Remember, we drew out the vector loop. We did the vector loop equation. Okay? We write it in its component form. Okay? We take the derivative with respect to the input variable. Okay? We then, solve for the Jacobian here by kicking everything to the other side, pulling out the first order kinematic coefficients, invert. This is Jacobian. We inverted times it. We got that. And then what you basically do is you could times both of these by omega 2. And we found that regardless of whether this is a first order kinematic coefficient that's a an angular one or a linear one, whether it's rotating or translating, you just times them both by omega 2, and we proved that will give you omega 3 and V4. It doesn't matter, right? You just times it by omega 2. Okay, so that's cool. So we've done velocity analysis, and now we've solved for the first order kinematic coefficients. Now how do we continue on and do acceleration analysis? Well, we've already got these equations, so why don't you take the derivative of this one again with respect to the input variable theta 2. So go ahead and put me on pause and get practice doing that. Okay? If you don't want to wait, by taking the derivative of this with respect to theta 2, you get that answer. And remember the product rule. Okay? Stare at that for a bit. If that's confusing, just refresh on product rule and chain rule. Okay? Now put me on pause and take the derivative of this equation with respect to theta 2, and I'll give you the answer in a second. Okay? That answer is this. Okay, hopefully you got that. Now move everything that doesn't have the second order kinematic coefficients in it to the other side and pull out the second order kinematic coefficients and find a matrix. Okay, you will find, if you did the correct answer, you'll find this. And notice this is the Jacobian that you confirm is the same as this. Look, it's magic. If those are different, you know you've done something wrong. So every time you're doing an exam, make sure those are the same Jacobian matrix, and you invert it, just like you did there, and you'll get these. Now notice, even though these vectors are the same, these ones are not. This one that you move to the other side, this is why you have to do this whole thing. Find the component form, take the derivatives, and move them over. These are the vectors that are important to solve, to know, so you can know what to multiply by the Jacobian inverse. Okay? Once you've done that, now you know these, and now you can plug it in these famous equations. Okay? And look, the difference in this example from the last example is that we have, instead of, in the last example it was a 4-bar, and everything was rotating. Omega 2 rotated, theta 3 and theta 4, they all rotate. But in this case, with a slider crank, one of the variables is translating. It's a linear thing. But there's no difference here. You have second order and first order kinematic coefficients that have a translational components. The derivative of the translation, R4, with respect to theta 2, is this one. And then the double derivative of that is this one. And you still multiply it by the same input. In this case, the input is an angular value, so it's omega 2 squared. And the input is an angular acceleration, alpha 2 squared. But what comes out is a linear acceleration of 4. Okay? And there's examples where the input may not be angular. It might be linear. And so I'll show you, here's all the cases. Remember from velocity analysis, I showed you a chart similar to this to look at the units of all the different combinations of first order kinematic coefficients. Well, we can do the exact same thing here for second order kinematic coefficients, okay? So say the input is angular, theta, and the output is theta. Well, that's like the 4-bar one. Then the second order kinematic coefficient is the second derivative of the theta j with respect to the input variable, which is also a theta. So it's dimensionless. It would be radians per radian squared, which would be 1 over radians, but that's dimensionless because radians doesn't have a dimension. Okay? This one, say the input is a translation and the output is a theta. Well, then what you have is the double derivative of the rotation, where the input is a length. So basically you've got radians per meter squared, and that's just meters squared, or 1 over length squared is the dimension. Okay. The other way you could do this is have the input be a theta and the output's a displacement, which was the slider crank scenario. And again, the unit of that second order kinematic coefficient, where you take the double derivative of it with respect to the input variable, it would be meters per radian squared, which is just meters or length, because radians is unitless. And then here's sometimes you can have input and outputs where they're both translations, a mechanism where you input a translation, the output's a translation. And the second order kinematic coefficient would be in units of meters per meter squared, which is just 1 over meters or 1 over length. Okay? So that's the second order kinematic coefficient for that. Okay. Okay, we're almost done here. Let's do acceleration of a point. Okay, so do you remember we did acceleration of a point for velocity analysis? We said, say we have a slider crank and we want to find the velocity of d. Well, to do that, you needed to solve position analysis totally, you need to solve velocity analysis totally, and then you needed to use the vectors and the information you knew to find the velocity of that point. And let's do a quick review of that. So remember, we solved everything, we know everything, so we're going to define RD, a vector that points from here to D, with respect to vectors we already know, which is R2 plus R5, okay, which is defined from there to there, okay, and we write that in component form. Okay, and we note that R5's theta is, theta 3 is from here to there. Theta 5 is theta 3 plus pi. Okay, theta 3 plus pi, because it's from its tail is there, we go around, it's going the opposite direction, and it's length d. Okay, and first of all, the first order kinematic coefficient of this, if you take the derivative of both these with respect to the input, pi goes to 0, so they're both the same. And by the way, if you take the second order kinematic coefficient with respect to both, you take the derivative of that again with respect to the input, you have to do the same thing on both sides. Theta 5 double prime equals theta 3 double prime. Okay, just FYI. Okay, but you've got those. Now what you do to find the velocity of these points, that's the position, is you take the derivative of those component forms with respect to the input variable, not time. And if you do that, remember you get this and you get that. Okay, so it's the derivative of this one with respect to the input, and the derivative of this one with respect to the input. Now you plug in all these things, and you see, we want to find it with respect to what we already found with position or velocity analysis and position analysis. So you want it with respect to theta 3 and theta 3 prime. Okay, and so you've got that. So great. And now what you do, if you recall, if you want to just find the velocity, is you take those prime, yd prime, the derivative of those with respect to the input variable, and you times them by omega 2. And out would come the velocity of each component of d. And you've got it. You got the velocity of the x component and the velocity of the y component with respect to time, and you're done. That was what we did for velocity analysis. But now we need to go to the next point. We need to find the acceleration of that point d. So instead of doing what we did before, let's take those things with respect to this form, xd prime, the first order kinematic coefficients of those, and let's take the derivative of them with respect to the input variable. So put me on pause and take the derivative of xd prime with respect to theta 2, and do the same thing with yd prime with respect to theta 2. Okay? All right, so if you've done that, I'll give you the first answer is this. That's xd doubled prime. So that's the double derivative of xd with respect to the input variable. The second kinematic coefficient, okay, of xd. And now you do yd double prime, and you get this guy. Okay. Now again, we didn't, we're still doing things with respect to theta 5 and theta 5 prime. So let's use this stuff down here to replace it, because when we did position and velocity analysis, we solved those with respect to theta 3 and theta 4, Yeah, we solve it with respect to theta 3 and R4, essentially. Okay? Because it's a slider crank mechanism here. And so we know all this stuff, right? So we plug in what we know, and check it out. From position analysis, you know this. From and this. From velocity analysis, you know the first order kinematic coefficients, and they gave you R5. That was D, right? And then you remember, to do acceleration of a point, you have to have finished acceleration analysis. You have to have already solved for the second order kinematic coefficients. That's key. Just like to find the velocity of a point, you have to have done all of velocity analysis, and you have to already know omega 3 and omega 4, for these things, the outputs, and the first order kinematic coefficients. In this case, you have to have done acceleration analysis. You have to know the second order kinematic coefficients, okay? Okay, and so theta 3 double prime. Okay, so now you know all this stuff, xd prime, xd double prime, yd double prime. And so now what we want to do is calculate the output variables. We want to find the velocity in the x component of d and the velocity of the y component of d. Okay, so remember, to find for velocity analysis, you just take the first order kinematic coefficients, multiply it by the input, and you get the output there. And again, if you take the derivative of these with respect to time, you're going to find the x double dot d, which is exactly what you're after, is the acceleration. That's the derivative of this, which is essentially take the product rule of this and this. You take the derivative of that times the normal one plus the normal one of that times the derivative of that. And recalling that from the chain rule, this is true, okay, because these guys cancel. Then you can take that and plug it back in here, and you end up getting our famous equation again. I just re-derived the famous equation for acceleration analysis, but for acceleration of a point, it's the same thing. If you have the second order kinematic coefficient, the first order kinematic coefficient, you multiply it by the input angular, the input value squared, and the input velocity squared, and the input acceleration. Okay, whether that's angular in this case or whether it would be linear, it doesn't. Whatever the input is what you do. And you do the same thing for y. Okay, and so once you've done position velocity analysis and acceleration analysis, you have all these the first and second order kinematic coefficients. You can plug it in here, and you get the velocity of that point. Okay, so we can lump it into this. Here's the x component right here. Here's the y component right here. So we do I and j for unit vectors, an x and y component. And you could also, interestingly enough, reorganize this. So you put the vector in I and j together that have to do with the angular, the acceleration vector. The angular velocity. The vector that has to do with that, and then you have the velocity that has to do with the angular acceleration. Okay, so you can just see we move this over there and move this over there, and we're mixing I and j's to find a vector that times by these components. And notice, of course, the second order kinematic coefficient is always the thing that multiplies by the velocity squared, and the first order kinematic coefficients are the things that multiply by the acceleration. Interestingly enough. Okay. So we're almost done. We can of course, that's the kinematic coefficient approach to finding the acceleration of a point, and that's the approach I recommend you do on exams and just kind of in your life. But you can also sometimes be quicker at finding the acceleration of a point just by using the acceleration difference equation to march from one point to another. And if there's stuff sliding on other things, like one link in a slot, then you're going to need to use the acceleration, the apparent acceleration equation as well. But for this, there's nothing like that. So if we want to march from here to there to there to there to d to find the acceleration of d, we could just do this. Okay, so the acceleration of a would be the acceleration of AO, which is 0, plus the omega 2 cross omega 2 cross R2, which is the normal centripetal component. And then plus alpha 2 cross R2, which is the tangential component. Add those two together, and that's A, the acceleration of A. And then you take that acceleration of A, you've marched to there, you go from there to there, you take the acceleration of A, which is all this stuff, plug it in, and take plus omega 5 cross omega 5 cross R5. Okay? And remember, omega 5 is the same thing as omega 3. They're the same thing. If you recall, we found the vector 3 when we did the vector loop. And that, of course, rotates the same as R5. Okay, so, this is the normal component, and then that is the tangential component, alpha 5 cross R5, which is also alpha 3 cross R5 there, okay? And so that marches from A to D. And if you have those values, you can plug it in and you get the answer. Okay. Okay, so with that, we are essentially done, okay, with the hardest topic by far in this course. The next few topics are much simpler. So please review this. These are summary slides that kind of review the entire lecture, how you find kinematic coefficients and how you use them to solve for acceleration analysis. I'm not going to re-lecture on it. And here's the acceleration of a point using kinematic coefficients. But please, what I want you to do is go through this lecture and listen to it a couple times. And you might want to read the book on this one if you're confused. And really internalize this and do a bunch of practice problems, because this is not simple stuff. But congratulations, you're done with the most painful topic. So we'll see you in topic 5.